When conceived in the 1960s, the Boeing 737 sat so low off the ground for easy loading that the bottom of the engine nacelles were flattened. By a procedure called grandfathering, Boeing was able to produce 4 generations of the aircraft without waiting for lengthy approvals. On the latest MAX version, the engines were too large to fit under the wings and had to be placed much further forward. If the aircraft tipped up too much, the airflow could impinge upon the upper inside of the nacelles and push the aircraft further upwards, causing it to stall and crash. To guard against this, Boeing added MCAS, standing for Maneuvering Characteristic Augmentation System, to push the nose down in such a case. This not only prevented the aircraft stalling, but also meant the aircraft could be made to handle just like previous versions of the 737. It may have been for this reason that Boeing did not explain the functioning of the MCAS in the manual or tell the airlines about it. Also, mentioning it would have highlighted the grandchild's possible tantrum. 2 737 MAXes crashed, seemingly because the MCAS pushed the nose down and the pilots were unable to overcome it in the limited time available. Few people know that an Airbus A320 crashed during an end-of-lease acceptance test carried out at too low an altitude. Workers hosing down the aircraft prior to the handover had allowed water to penetrate deep inside the mechanisms of the angle of attack sensors. These froze in position at the same angle when the aircraft reached 31,000 feet. This meant that when the pilots carried out the stall protection test much too low, it could never work properly. When the stall warning finally sounded, the aircraft was flying much too slowly, and when the pilot pulled back on his side stick, the elevators could not overcome the combined effect of the pitch trim set at its maximum nose up and the go-around thrust of engines set low down under the wings, also levering the nose up. Neither pilot seemed to have noticed used manual pitch trim that also appeared in amber on the primary flight display. Only 62 seconds had elapsed between the time the A320 stall warning finally triggered and the moment the CVR recording stopped, with the aircraft plunging into the sea in the south of France. Though the circumstances and conditions were quite different from 737 MAX crashes, what they do have in common is the lack of time to deal with the trim. As described in Chapter 18 of our book, Airbus, unlike Boeing, was relying on the idea that 2 sensors out of 3 showing the same reading must be right, which normally is the case. In the XL Airways A320 case, there was nothing preventing the pilots manually adjusting the trim. They did not notice the warning and, of course, did not have much time, having performed the tests much too low. For Boeing to only rely on 1 sensor seems unconscionable. Airbus were relying on 2 out of 3, and the problem, water in the sensors, was a freak one. Boeing are between a rock and a hard place. If they redo the software so MCAS only functions when the 2 angle of attack sensors concord, there's a danger the system will not save the quirky aircraft when needed. Should having 2 sensors concording feature on the MEL, the minimum equipment list? Should there be 3? On April the 3rd, Leham News published a piece, see link below, saying how the Wall Street Journal confirmed the Ethiopian pilots did indeed use the cutout switches as prescribed by Boeing and the FAA to stop MCAS. But this did not suffice, as at too high a speed, the pilots did not have the physical strength to manually overcome the trim. In the comments to the Leham News piece, someone said Boeing were trying to graft modern software onto an airliner from an earlier era, resulting in incoherence, with it impossible to take advantage of what a modern integrated fly-by-wire system could offer. Thank you.